Mhm. Yeah, okay. Good. So today we will discuss a paper called V-JEPA 2. V-JEPA opens as a Visio joint embedding predictive architecture, and it's the third model of a JEPA series. And the main goal of those models is to achieve uh, world model related architecture with self-supervised pre-training. Uh, one of the member of these uh, paper's author is Jan Lagun, who pushes the agenda, who pushes the argument that the real world model should be achieved with observing the surrounding. By world model, we mean the model which understands physical dynamics, which understands um, different object interactions and can have some predictive abilities for the next state, like human do, and it is not achieved by a language. In contrast to different approaches where they use language scraped from internet and with autoregressive try to achieve some foundation model. Uh, the JEPA first paper was released several years ago. It's called iJEPA, and their main insight is that to achieve general foundation vision model, uh, like I mentioned, it should be achieved by observing a surrounding, and in this case, they proposed image-based JEPA model in their first approach paper, which basically converts the image from pixel space into some representation space and tries to predict the mask tokens in this representation space only. So instead of using pixel space like my architecture does, they try to predict the missing parts, but only in internally learned representation space. And afterwards, they continued their path in this direction and proposed V-JEPA. It was the paper published last year, which does basically same thing, but for video input. This is the basic architecture for it. They tokenize the video frames, mask its tokens, its patches, generate the representation space for non-mask patches, and try to predict the mask tokens from this embedding space with teacher-student architecture.
So you predict the tokens.
Yeah, in contrast to other self-distillation approaches like Dino, here they are trying to predict the tokens, like in iJEPA also. But in this case, they are doing basically the same things for video, and while masking, they mask all the frames with the same location, uh, which is very intuitive because if some patches are not masked in a certain frame, then uh, the reconstruction task will be very easy. So it makes the problem a little harder, and due to which the model learns very important features during pre-training. Okay, and today we will discuss the V-JEPA 2. I would like to show the several minor demonstration of this model. So it's their main page of from Meta AI. This is some demonstration of V-JEPA 2 after fine-tuning. The left example is regarding the video understanding. One moment. I think we have a very slow internet. And yeah, it uh, overall understand the word, the physics, and the video content. And the right part, they fine-tune it by mm, asking the model what would the person do next. It's called action anticipation task. Like before doing the action, the model should predict in their example 1 seconds away what will be happening in the video.
This is what Boris was saying yesterday, but for the future action, not the past action. Okay.
What is? Yes, sure.
Okay.
Mhm.
So, and the actions are text, so it does not generate images. It takes the video stream.
Yeah,
Yeah,
but it's not integrated in a VIT architecture. It's completely different block, which is fine-tuned with frozen Pegman. And here I saw a different post regarding this JEPA. And they released a Hugging Face demo, which is basically fine-tuned it. They're fine-tuned the V-JEPA 2 on a dataset called something version 2, which is uh, action recognition model. Like it doesn't understand the object, but understands the action. That's why there is something here. The squeezing, moving something down, pretending or trying and failing to twist. Okay. All right, let's dive into the paper. So this is basically the whole structure of today's paper. They first pre-train V-JEPA, the previous V-JEPA model, but already in this case, very large data set. And with different parameters to understand like how much V-JEPA can be scaled. Afterwards, they try to demonstrate its ability by fine-tune it on the tasks like video question answering, action classification, object recognition, action anticipation, like the one I just showed. And moreover, they uh, introduced additional block on top of V-JEPA and kind of fine-tuned it after the pre-training with a very small amount of unlabeled robotics data and showed its uh, robot manipulation ability in a zero-shot manner, independent of the robot type, in a pretty unique way. I will talk about it a little later.
So when it says 1 million hours,
Mhm.
it's a lot, right? Do you know how quick they sample from video, how many frames it becomes?
How many? Per sample is basically for at least 4 seconds.
One sample
One
is
sample, one video sample is at least 4 seconds.
4 seconds. How many frames?
Yeah, yeah, yeah. In their pre-training, they achieved the best result with 64 frames per sample.
64 frames per sample, which is if it's 4 seconds, it means 16 frames per second.
Yeah.
It's a lot.
Mhm.
But if you have 1 million hour,
Mhm.
what is my calculator? 1 million hour times 60 minutes times
Mhm.
60 seconds
Mhm.
times 16 frames.
Yeah, their pre-training dataset is about 20, 22 billion, I believe. Yeah, it's their dataset size is 22 million video.
Videos.
Yeah. Mhm.
My calculation becomes 50 billion frames.
Mhm.
It's okay.
Yeah. GPU. Oh, sorry. It's something other. Don't look at this.
GPU days.
Training GPU.
What's the axis? 10 to the fourth.
10 to the fourth. Yeah, sure. So their final pre-training is this one, double one, which is about 10,000 GPU days. Uh, with respect to 100 GPUs.
With 64 GPUs, it's
27 years.
but with
Okay.
64 GPUs,
Mm.
half a year.
Mhm. Yeah, sure. They actually also spend a lot of training for hyperparameter tunings, etc. So
It's not terrible. I mean, it's not even GPT-3. It's not.
yeah, and
It's a
it's
little bit more than we can do next year, but
mhm. Okay. So let's talk about what they improved in V-JEPA 2 compared to V-JEPA. First of all, they scaled the dataset size. Like in V-JEPA, they used 2 million videos, and in this case, they pre-trained on 22 million videos from various sources, both curated and uncurated datasets. Uh, they also pre-trained it with larger VITs. They scaled it up to VIT G, which has around 1 billion parameters. They also leveraged the warm-up constant decay for their different hyperparameter tunings and scaled their training up to pre-training up to 252,000 iteration. Also, they utilized higher resolution input images. In this right part, they evaluated their pre-trained V-JEPA 2 by frozen fine-tuning it on 6 different benchmarks and afterward calculating their mean accuracy. And they show how each improvement improved overall. Yeah, how it helped them to improve the model, the features. So the first one is the standard V-JEPA one. As I mentioned, they enhanced the data set about 10 times, which helped a little, about 1% in on average accuracy. The model scaling from VIT-L to VIT-G. VIT-L has 300 million parameter, VIT-G has 1 million. This is for longer training, like making the pre-training continue about 3 times more iteration and with higher resolution images.
So in video understanding, resolution is total.
I think it's everywhere. It's
No,
always a
in
bottleneck.
satellite, for example, you don't have high resolution.
Yeah. But if you try to classify object, it's always better to have.
That they have their videos are larger resolution and they resize, and now they don't resize, right?
Yeah. Yeah, I get it.
And maybe this increases the compute a lot because you have more tokens frame.
Yeah, and that's why they leverage warm-up constant decay and use the higher resolution only the decay phase.
Okay. Okay.
So let's talk about the pre-training data set. They used the video data set from various sources, how to 1 million, etc. Something version to also exist in their pre-training data set. And also they added a YouTube video, which is called YT tempered 1 billion, which is actually not curated generic videos from YouTube. However, utilizing it in their pre-training with the other pretty curated datasets is not a good idea. Therefore, they try to curate this dataset like the Dyna version 2 did. So in this table is a summary of their all pre-training datasets. The first 4 are video dataset. They also utilized ImageNet, just images. And they curated YT tempered 1B dataset. Let's talk a little about it, how they did it. Let's see here. Yeah. So YT1B, they first removed all the videos that has a shorter length than 4 seconds. And afterwards, they retained only 370 the million videos. Yeah, it's YT 1 billion. And here they try to curate this data set. So after removing all the short videos, they applied Dyna version 2 VITL model for calculating each sense embedding. They do it by applying Dyna version 2 in the middle frame of each video and consider the constructed embedding as the embedding of the whole video. After calculating all the embeddings for all the videos, they apply k-means clustering and get 1.5 million clusters. However, after clusterization for curating this dataset, they utilized the remaining dataset that existed in their pre-training, which they consider already curated dataset, and try to curate this one with the help of the other one the following way. First of all, after clusterization of YT1B, they assign each sample of the data points of the remaining data sources with his or her the data points corresponding cluster of which is one of these clusters, and remove the clusters where didn't exist any kind of data set in it.
So you have 1.5 million clusters. In 200,000 of them, there is one video that is from better dataset.
Yeah. These four are the better data sets,
Okay.
which are their kind of target distribution that they try to mimic. So from this 1.5 million dataset, only 200,000 clusters contain one of these data points. And they only keep those clusters. And afterwards came how to sample from those clusters. They assign manually each data source a retrieve weight, which is basically based on their amount of data in it. It's pretty similar to the ratio of the dataset size and the retrieval weight. And based on those weights, they calculate the weight for the final for each remaining cluster from these 210,000 clusters with the following formula. Here, for each fixed cluster, they calculate the sum of retrieval weight, which is one of those force for each cluster, multiplied with the amount of data set exist in its cluster from this target data set, and divided the whole number of scenes. So the capital D is in this case 4, and they iterate between each of these 4 dataset, calculate this ratio and multiply it with their corresponding retrieval weight, and calculate their overall sum to get the WC. And it's done for each cluster of this final curated dataset. So after curating this one YT1 billion, they try to pre-train their final model. Here we can see pretty interesting results. The left part is the pre-training of V-JEPA. All right, so about the left part, we actually already talked a little, like it shows how much the data scaling helps their overall accuracy and accuracy for each of those 6 downstream tasks. And the right part is showed how the performance changes with uncurated and uncurated dataset to show that the curation of YT1B actually helped them a lot. And the interesting result here is in the right part, they pre-trained it only on YT1B uncurated and only on YT1B curated datasets. And we can see that only training on YT1B curated dataset in its average score had higher value than if we pre-train it with this curated one plus the remaining ones. It's the left part. The VM 22 million is this overall pre-training dataset together with curated one. And in this specific example, when they pre-trained VITL, the results were a little interesting because by training only on curated 1T1B, achieved a little better result than pre-training on the overall dataset, which also contains the curated dataset. And they explain it that this uh, a picture changes when the model scales. Like if they pre-train for VITG, it's not the same. But in VITL, uh, only training on curated achieved better result.
So in VITG, the left one becomes better.
Yeah, the left one becomes comparably better than the right one here.
This one. Downstream task. Downstream task. Yeah.
Downstream task size, why?
This is
Yeah, I get it.
this.
Hmm.
Okay.
This is crazy. So both charts have the scale from 70 to 100, but somehow they're not equal in the paper.
So this is regarding the scaling model size. And for their pre-training, they used warm-up stable decay. I will explain why in the next page. Actually, here we can, this graph summarizes this whole paragraph. The left one, they show how model scaling helped overall average accuracy from 300 million to up to 1 billion parameter. In the middle slide, they show how much compute they will save if they uh, if instead of pre-training only, for example, in the third chart, when instead of pre-training only in 64 frames, they can train on shorter frames in the stage of warm-up and stable in the learning rate schedule, and only use the 64 frames in the decay part. And the same with using the 32 frames or 16 frames. And the right part shows how much benefit they get when during pre-training they use large number of frames. And even this helps when during fine-tuning they only use 16 frames. Like it also, they show that it's also beneficial to pre-train 64 frame clips and utilize its weight for 16 frame clips tasks. And they didn't get any additional effects when they tried to pre-train on the longer frames, like 260, the 256 or up to 1000 frames. So the 64 frame for the video pre-training was the optimal value for them. So yeah,
Is it always 4 seconds or is it longer?
no, 4 seconds is the minimal amount of
So it
length.
means that even for longer videos, they take only 64 frames.
For longer video, yeah, they just crop the 64 frame from it.
No.
Is it the
Yeah.
total number of frames or the frames per second?
No. The frames per second can be changeable, but the total number of frames is up to 64 frame. So the shortest duration is the 4 second, but the longest number of frames is 64.
But it means that if it's like 1 minute,
Mm-hmm.
it becomes like very like 1 frame per second, right? That's why my calculation didn't work. Which is something.
Maybe they split the video into many samples with 64 frames.
Yeah, if it's 1 minute video, okay. Okay.
So this is the pre-training.
Yeah, it's the pre-training, how they pre-trained V-JEPA 2 and achieved pretty good result when they compare it with the previous generation model V-JEPA.
Interesting to know that the left picture here is kind of a scaling, right?
Mm-hmm.
Would be interesting to know if by having the ITB even smaller ones, one could predict where it would get with the ITG. I don't look like that to be honest.
Okay. So the third section is about the robot, like how they try to use this model for robot manipulation tasks. They added additional block and called their new model V-JEPA 2 AC. AC is here as action condition model. But the main issue in this case, they tell that for planning, for predicting the next action of robots requires autoregressive reasoning, which lacks their pre-training. Therefore, they add additional block on top of it, additional predictor block, and try to add this autoregressive functionality in this block only. For training, they use Droid dataset, which has topic common videos from 3 to 4 seconds long and has 7 degree of freedom actions. And it's not there is no any instruction, it's just a robot hand doing some different actions. And the only annotation in this video is that each frame has the state of this robot. Like the state, as I mentioned, is consist of 7 degree of freedom axes. The first three are their its position. The second three are their orientation, the angles, And the last one is whether it's gripped or not, the gripper state.
Can you zoom in?
Yeah. Mhm.
So it is a lot of videos where the robot is doing something and we have every number about the robot state, where it is.
Yeah.
Okay, 62 hours.
Mhm.
Okay.
So as a model input, they denote xk as the input frames. Sk is the state in which the robot is in this frame, like the 7 numbers I just mentioned, its position, its orientation, and the gripper state. And from Sk, they can get the values for Ak, which is what action did the robot do for shifting from Sk to Sk plus 1. It just the delta state. Is it clear so far for the model input? Which one corresponds which? Xk is the frames, Sk are the states for each frame, and Ak is the action which can be calculated from Sk just by calculating the difference between adjacent Sk, like the difference between Sk and Sk plus 1.
Yeah, so if I'm here in the first frame and then the next frame I'm here, this is the action.
Sure.
Vector.
Yeah. The delta is its action. And they construct the input data set AK, SK, and ZK. And the main objective is based on these three. Also, ZK corresponds to the JEPA representation of XK. ZK is the output, the feature when we pass frame to the JEPA. And based on these three these three inputs, the autoregressive part of the additional block will try to predict the ZK plus 1. If we show it in the picture, so this is our video. We pass it through our JEPA network, which is frozen, and get the corresponding Z. For example, in this case, the Z0 is the following. We add additional AK and SK, the current state, and what action it should do to get to SK plus 1. And the predictor, this additional block, should try in autoregressive way to predict the next Z, which is this one.
So Z is just a vector.
Z0 is the token is the output of the first frame of
So
JEPA.
these are vectors.
Yeah, these are vectors.
And that's what we want to
It's the representation vector of each frame.
Okay, so the loss for the autoregressive is not really softmax because
No,
you are
No.
trying to predict the vector.
it's
Errors.
yeah. They utilize L1 loss,
Okay,
this one,
okay.
which is basically what I just said, the output of predictor block. And it's the difference between the output of predictor block and the JEPA output of the future frame. So why it's autoregressive here? Because from Z0 we are trying to predict Z1. From Z1 we try to predict Z2. And the prediction is done based on these two states, not states. One is the robot current state, and the other is what action the robot are trying to do to and we are trying to predict Z1 after this action.
Okay, so you want to predict what the camera will see after I do this action.
Yeah, it's not done in a pixel space, but it's done in the JEPA representation space.
Use X mask.
No.
X, no. We already did it in the pre-training phase here, and in this case, not in the mask.
If I understand what it's, how
Yeah.
we get that from.
That we just pass the frame through
Ah,
this JEPA. And that's all.
does this frame encoder use all the frames before?
What kind of frames?
Like for V2, does it use only the second frame or all the frames from 0 to first frame, second frame?
Yeah, good question. Inside this frame encoder, which is
Yeah.
frozen, it is bidirectional.
Inside frame code of this folder. Yeah, it good question. They pass it one by one. If that's what was the
Oh, okay.
So it doesn't have information about.
Let me check. No, actually, it doesn't see the previous ones. It just XK pass through the encoder.
Yeah.
Okay, K is this time limit.
K is the current frame index, and K is up to 16.
Predicting one frame at.
Yeah, sure. It tries to predict what frame will be after applying this action. And the action is the input of predictor here. And they also add the rollout loss, like in the left part is teacher forcing. It's called teacher forcing, like for each prediction, we compare the predicted Z1 with the ground truth Z1. But in this case, they let the predictor to predict the several upcoming frames, and just afterward to compare the predicted frame with the ground truth one.
Okay.
Like in this case, the predictor will try to predict Z1 and pass it to our next input without calculating the loss between these two. And give input the predicted one, not the ground truth one. And we'll again apply the same step several times. And after fourth step, and after only fourth step, we will try to calculate the L1 loss between the ground truth and the predicted one, which is called the rollout loss.
It's like without teacher forcing, like it would have worked if it was softmax, right? Because it works because there is no argmax.
Yeah, it's a regression task.
Yeah, so you take whatever vector it
Continuous
predicts,
space.
use as an input.
Yeah.
So you don't lose your computation graph, right? You can go with gradients through this.
Yeah.
Wow.
As the final loss, they calculate the summation of the teacher forcing and rollout loss. In their experiment, they use for rollout, they use just 2. So it just tries to predict just 2 steps ahead, not 4 or longer. Mm. And the question is like how do they utilize this functionality for robot planning? Like in this case, they try after aggressively to predict the next state, not the next action. But for robot manipulation tasks, the main objective is to predict the robot's next action. What should it do? Not what will be its next step. To do it, they suggested the inferring mechanism called actions by planning, which is the following. They for each task, instead of language instruction, they have the goal image, like in what state will be the hand after applying some action. And they try to generate the actions based on just seeing the final goal image and the initial state. So for each task, they have its starting state, starting image, they have the goal image, and they generate their representations correspondingly, like zk is the representation of xk and zg is the representation of xk after passing it through JEPA. And their main objective, which they call goal conditioned energy function, is to minimize these L1 loss by changing actions. Like
The sequence of actions.
In this case, our main objective is in what sequence of actions when we start from zk state and is from zk frame and sk state. After applying this sequence of action, we will get a similar state to our goal image. For example, in this case, let me show.
P there. Model.
P actually is this predictor.
Oh,
So the goal of this predictor is to predict the next state based on the action and state. So they say if our model should reach from here, from Z0 to Z4, for example, which actions should be applied here so that starting from here, we will generate Z4.
okay. So if we had a lot of resources, we would try all combinations of actions,
That is a similar thing, yeah.
and we would ask this predictor what will happen next, and at the end we think what predictor thinks will happen at the end and compare it to our target goal image.
Sure.
Okay.
So before talking about how they did this search for action, this is the demonstration, the start frame and the goal frame. There is very little change actually here, but there is a change. Like starting from here, what actions should be applied so that we will get this frame, the representation of this frame. This is another example, this is another example. So instead of language instruction, the task is described by just the goal image. For picking the right action, they use cross-entropy method, which basically says that let's start by assuming that each action has some Gaussian distribution from zero mean and one variance, a random sample from it, apply it, calculate the loss, and do it several hundred times, get the best action sequence, and update the distribution, and do it iteratively. Like, for example, if we are trying to predict just one action, we will try to sample from standard distribution, apply this action, calculate the loss, and do it, in this example, about 800 times. Pick the top 7 actions that generated the best energy loss. This is the energy loss. Update our distribution parameters based on these top 7 actions, and do this iteration about 10 times, this refinement step 10 times. Again, sample from already updated distribution, apply action, calculate the energy loss, and update the distribution parameter.
When you say distribution, it is distribution over actions?
Yeah, over actions. We sample the action coordinates at each point in the planning horizon for a sequence of Gaussian standard distribution. So the action consists of 7 values. Each value has its own distribution, I believe. And every time they sample for each value and picking the top actions, try to update the distribution and apply this refinement step over and over again to get the final distribution for each action. Before applying each step. It's not a realistic way to apply large models for robots, but it's some kind of evaluation method to compare different vision models.
So if I know what is going to happen next if I do this action, that's my peak prediction.
Yeah, here you have a kind of vision.
I have my current observation. I want to go to goal. I'm putting some initial distributions over actions. Okay, actions are continuous. So you can go left, right.
The delta x, delta y, delta z,
Okay.
delta angle.
So I thought it's discrete and I was trying to find what is uniform here. So it's not uniform. It's if you start from normal with zero mean, it means that on average you will not
do anything.
But then you might move left, right, this axis, and then 6 axis like that, right? So you sample from this initial distribution. You make the move.
Calculate this energy function, then pick the top 7 actions that brought you the smallest energy function, and based on their values, update your initial Gaussian distribution mean and variance values.
Only mean and variance. So
Yeah, only mean and variance.
That's the main Gaussian.
Yeah. And do it iteratively, for example, the same thing 10 times. In their ablation study, they did this refinement called step 10 times to get best distribution for action.
do actions have a limited range? Usually robots can do.
Large actions?
Yes.
Actually, that's a good question. It's they constrained in their experiment the action. In this case, the action is constrained with a radius of 0.075. Like the distribution.
So it means they use truncated
Yeah.
Gaussian distribution. Okay.
So each time it does a very minor step. And they show how each step makes the position error lower and lower for each position axis, delta x, delta y, and delta z. And one additional interesting graph is this surface. It's a surface of the energy function. Let me also show its caption.
Get the equation y.
Like in this example, they stated that to reach the ground truth image, the robot should apply delta y minus 0.1. This is the surface of energy function when the delta z is 0. In this experiment, they fixed the delta z 0, and how much will the energy function change based on delta x and delta y. And the ground truth action should be minus 0.1. In this graph, they show that the minimal value of this surface will be achieved for delta x 0 and delta y 0.05, which is pretty close.
Okay, so you essentially with this Gaussian and stuff, you are trying to understand this surface and find the minimum
And there's
point.
so it's a good surface also. In this example, for example, that the lowest, the minimum value is pretty close to the ground truth. That's why it's a good idea to explore this space. Yeah, this is the sentence that just highlights what I.
So when you say you do sampling, then you do inference many times, you pick the 7 best, right?
Mhm.
How many times do you do forward pass now?
Forward pass
You
from
don't even do forward pass because you are operating in the frozen regime.
the forward pass from predictor or from JEPA.
JEPA I was asking, but looks like
You
JEPA.
just use JEPA for
Initial and last.
the initial observation and the goal image, that's all.
Okay, so
Afterwards, you only use the predictor
no
function.
predictor.
Yeah.
Okay, so I give this one predictor the initial JEPA state
Mhm.
and some sample of action from this distribution initial. I run this autoregressive, find something, compare it to compute energy, and then I need to do it many times to get 7 best. It's almost like GRPO, right? Because you're taking the best ones and then updating your initial distribution, not even your model. you update your initial distribution, and then you repeat
You
it. And now
repeat it. In this case, they did 800 times sampling. For overall 800 sampling, they calculated the top 7 of them. Then they refined the distribution, refining step. Refine distribution. And do this iteration 10 times.
Okay, so if you do 8,000 forward pass for this small model, we will get a relatively good distribution or already good actions from this distribution. Okay, I can take the top 7 of the very last iteration. These are good actions.
Yeah.
So now I can do robotics with this. So for predicting my next best action, I actually need 8,000 forward passes, but for a very small model.
Yeah, just using predictor block. This is kind of zero-shot robot planning because there is no any kind of gradient descent optimization or training, which they use to compare their model with the remaining world models.
I see. So they should have some sort of robotic benchmark, right? Oh, no.
Yeah, sure.
Just like our PLN.
Yeah, it's.
But there is no, okay, so how do we compare? We don't have text here, the notice part. But you can give the.
You can give just the initial frame and the end frame, and that's all.
Okay.
It actually shows how much they don't use language models in their experiments and even in robotic benchmarks, just using the image. The experiments we talked so far are pretty basic experiments. They try to make a little challenging manipulation tasks, which are separated into 3 categories: grasping, reach with object, and pick and place. And for making the model to be able to achieve both picking and places task in one planning, they added 2 additional sub-goal images. The first, for example, in the grasping, they just, for their goal image is the final image where the robot already grasps something. For reach with object is just again one image where it reached with some object in it, and pick and place can be divided into 2 sub-goals. So besides the final goal image, they also add an image that shows the object being grasped and some additional goal image which shows the object in the vicinity of the goal position. Let me show this part. So each line is a separate task of pick and place. So the robot should move, pick the cup, and place it on top of the table. And instead of providing only the final image, they also add this image and this image. The first image is when the robot grasps the cup, and the second additional one is where the cup is in the vicinity of the final location. So instead of trying to achieve one planning starting from here to here, they divide it into 3 subtasks. First, it will achieve here with this sub-goal image. Then it will try to achieve here, guided by this one, and the final image. Let's show more examples. This is the grasp cup, the first category of task. Sorry. This is the starting frame and the goal frame for grasping cup. Again, starting and final goal image. This is some example for reach with cup. Starting frame, goal frame.
So they have baselines for this.
Yeah. And this is the pick and place. Starting frame. So instead of just the goal frame, they add 2 sub-goal images.
So you to train their model to decompose into subgroups. Like create subgroup, predict subgroup, and just run code.
Okay. Yeah, they compare it with 2 other models, the Octo, which is visual language which is visual language action model, I believe. Yeah, the Octo is visual language action model, and also some additional model, word model called Cosmos, which is again from Meta, as released several months ago. It's I believe is a diffusion-based video generation model. This is the results. This is the Cosmos.
Cosmos is NVIDIA.
Meta. Console Meta.
The Cosmos that you are saying on is from Microsoft.
Oh, okay, NVIDIA. Yeah. Okay.
So, to the table again.
This one? Yeah.
Very beautiful number, 20%, 50%.
Mm-hmm. They also explained that because Cosmos model is very slow, much more slower, that's why they apply more sampling steps for JEPA to compare it. Like for each robot skill, we evaluate each model across 10 tasks with 87. It takes 4 minutes to compute a single action in each planning step with Cosmos. 4 minutes.
Yeah, because it probably runs diffusion to generate the pattern.
Mhm. And let's go forward to evaluate our JEPA model, not the JEPA AC, but JEPA model for motion understanding, the video question answering, etc. So in this section, it shows its ability for appearance understanding and motion understanding. In motion understanding, it achieves state-of-the-art result. In appearance understanding, it has some competitive results. And these evaluations are interesting too. What they did, at least for me, a unique way. They again they froze the JEPA model, added 4-layer predictor block for a downstream task, which is fine-tuned, but for classification purposes, they utilize separate learnable query token. Like the last of the self-attention block of the additional model is replaced with cross-attention layer with a learnable query token. I don't know why they did this way, but here is the basic architecture. This is their JEPA. This is the 4-block the predictor, and there is one learnable query token which does some cross attention for these features. And afterwards, they apply softmax or whatever on top of this learnable query. Okay, let's read this part to stall. They used both video-based and image-based visual encoders for this benchmark. They also highlight that for one more thing to mention, that all these evaluation benchmarks are for video inputs. So to utilize them for just image-based visual encoders, for they generate frames or representations separately and then concatenate them together. And afterwards, pass this additional block.
Okay, so sometimes Siglip is better than Diga.
Yeah,
Not in the motion understanding, but better in appearance understanding.
yeah, and Stiglip didn't see video, I believe.
No. Comparing it to Dino.
No, I'm saying it's the best result from all the models. Oh, okay. Yes, it's just a person understanding, not motion. Yeah, and this one is Eclipse 2. It's the newer version. Yeah, I didn't notice that.
So their system even at V80L is very good.
Mhm. Okay. So moving forward, the next benchmark is action anticipation. This one is a little more interesting. Like for benchmark, they used a dataset called EK100, which is the video of cooking dataset, overall 100 hours. And for each sample, it has labels for its actions, which is consist of verbs and nouns, whereas total 97 verb and 300 noun categories. In this case, instead of using just one query, oh, okay, let's not talk about this. Yeah, so in this case, instead of using just one query for classification, because it's actually classification task, it's action recognition, action anticipation. We will talk about what happens here, but in the end, they use three queries, three learnable queries. The first one, all of them are integrated with cross attention with the predicted block, the probe attention block, with these words. The first one tries to predict the action, which is both the noun and verb together. The noun and verb. This one tries to predict the noun. This one tries to predict the verb. So basically, this one is this and this one together. And for evaluation, they use the method called recall 5, which is basically they are picking the top 5 prediction of the predictor, and if one of them corresponds to the ground truth, then the model predicted something right. Recall 5. So it measures whether at least one of the top 5 predictions corresponds to the ground truth or not. So the task is from a given video, it should try to predict 1 second ahead what action will be applied. Like after 1 second, what action will be happening. To be able to solve this task, they pass the JEPA, which can take video inputs, the frames, the observation frames, like what it should see, and based on them, it will try to predict the future stuff. And they also try to predict the future frame with JEPA, just passing the masked frame of 1 hour ahead. Like the JEPA is masked visual model which can predict the masked part of the visual. The JEPA has its own predictor here. Yeah. So in the left part is our JEPA. So as an input, they pass the observation frames that none of them are masked, and the upcoming frame masked. And with this predictor, which also is pre-trained with JEPA in its pre-training stage, it will try to predict the upcoming frame. And they concatenate the prediction with the observation frames and pass it to the decoder block.
Okay.
Here to show how it articulated this part. The predictor takes the encoder representation along with the mask tokens corresponding to the frame 1 second into the future and predicts the representation of the future frame. This is done just a predictor head of the JEPA to predict the representation of the future frame. Afterwards, the outputs of the predictor and encoder are concatenated along with the token dimension and fed to the attentive probe. Attentive probe is 4 layers.
Okay, so you first pass it through JEPA to predict
this,
the next frame.
to predict
1 second later, what will
this
happen?
frame.
And then
Afterwards, they take this and they take this
we give it as an input.
and give it 1, 2, 3. With this one, it becomes this one 4, 1, 2, 3, 1, 2, 3. And together they pass through this attention probe. And with these additional 3 learnable queries, it will try to predict the future step.
What happens fiction and the noun and verb don't
Yeah, there are some cases where
match?
the action differs from the noun verb. It's just additional supervision, I believe, just technique to help it move, learn faster.
Do they always take the action as the output?
I don't know.
It's crazy. So if you want to predict what was the action before, not anticipation, but recognition, you would give the video as an input, you pass it through JEPA and give it to these 4 layers and predict. So now if you want to go to future, you first predict the future and
in the representation space.
And tell it to
Yeah.
It would be interesting to see if what would happen if you didn't predict the future with JEPA. That would be the baseline, right? Like if you could train this entire thing without this additional mask prediction.
I think they did it and didn't work. That's why they shifted to this. But how will you supervise it?
You have the labels, right?
So just pass the representation of those three to
Mhm.
the predictor.
So in that case, the knowledge about the future will come from these 4 layers.
Yeah.
But now the information about future comes from JEPA.
And here are three examples. The first two examples are success cases. The third one is the failure case. Like based on these 4 frames, it predicted its top 5 predictions are wash sink, wash side surfaces, turn on water, rinse sponge, clean wall. Wash sink. The second one again, put plate or pickup plate. A put plate. Put glass, close door, etc. Nice. Yeah, and finally the video question answering task, where they are trying to compare their JEPA with other vision encoders of visual language models. And the last sentence is pretty interesting, which aligns with our research. That this is the first work that they're using the vision encoder without language guidance and train it for a multimodal LLM and show that it sometimes outperforms the other remaining visual language models. So this is the comparison. In this case, they apply the same strategy like in lava paper, where for a given LLM, they are trying to integrate VIT into the given LLM by first trying the projection layer and then applying the overall training with frozen encoder. And for this experiment, they pick as an LLM going to 7B instruct and constantly change it. I don't know. But constantly change its vision encoder with remaining vision encoders and do this language vision aligning instructions the following step with frozen vision encoder on a small data set. By small, I mean not very small, about 18 million images of video text pairs. So instead of comparing their JEPA with other VLMs, they suggest a framework of comparison, pick a fixed LLM, align the vision encoder with this given LLM, and do evaluations by changing vision. They train both the projection and the LLM, but with frozen vision encoder. And again, all of those tasks are for video inputs, not just image, where they achieve pretty good results compared to the remaining architectures. And in these are done with small experiment, but afterwards they also showed that their JEPA can be scaled up to VITG 512 resolution videos. And finally, they integrate their JEPA with Llama 3.1 8B and create their own vision language model, a visual language model in this case, and compare with the remaining already pretty popular vision language models, and showed that for video understanding benchmarks, their visual language model got state-of-the-art result in the number of benchmarks where their vision model didn't pre-trained with language supervision at all, just with self-supervised just image supervision. And they did this pre-training with 88.5 samples. This is the last page of this paper.
The question regarding the training of the V-JEPA tool. They used the ImageNet that consists of 1 million images.
Yeah.
And I wonder, was it really influential, and did they do the evaluation study? Why they ever need those 1 million images when they have lots of videos?
I don't think they did this kind of population study.
It's just 1 million images.
Yeah.
So
1 million images actually has a slight higher weight, but actually each image here corresponds a separate video. Like for image net, they to consider them as videos, they just repeated the image together several times to consider them as, for example, 16 frame video.
that's how they use. I thought they just predicted
Yes.
advanced tokens, and that's all, but they duplicated.
Yeah. Here.
Interesting.
Do you have more questions?
How can we use this for VLN?
If they released the VLN version of their JEPA with Llama 3.1b, it can be interesting baseline.
But they only used video then text, right? They didn't use text, video, action. So probably that part is on us.
Yeah. I don't believe that QNVL also used the interleaving way of image, text, image. It just in there in its pre-training, so just video frames and text, like the JEPA.
But I think their non-text action system is also interesting, right? Like, can we use it in pre-training with our, like, imagine you create random trajectories in this simulation and generate lots of data without instructions.
But you mean by predicting the action with goal images? Because it's not applicable in our case.
Yeah, no. Yes. But some sort of pre-training on lots of simulation data. I think there is something important here that it can predict the next frame. What was the name for these 4 layers?
Actually, there is one predictor. Is trained in pre-training. There is again a predictor for a different predictor for JEPA IC, which is the next state predictor. This is the one. Is different predictor, and there is a 4-layer decoder block which is called probe classification or probe action anticipation.
Something around this probe.
Attentive probe. Anticipation.
So in our case, next action always depends on instruction. It is not. Okay, now I can formulate what I mean. So we don't need the LLM because we just generate the text. We can bring the input text instruction as an additional input to these 4 layers. And then use these 4 layers only to predict an action. So imagine we have instruction. It goes through the bed. I don't know what is the modern version of it. It gives me some representation. Then I have a video of my previous states. This is the video. This goes to JEPA. It gives me the states for this video. And now I have these 4 layers conditioned on text and these 4 things and predict action. I don't need text decoder.
Yeah, but what about its previous actions?
Good point. I think one of those versions had it, right? Which one was that? Can you go up? Maybe this second predictor that we showed.
You mean this autoregressive one? Is
These blue points were actions, right?
yeah. But it uses the JEPA only once.
You can also use it once.
But what about the upcoming observation? Like after applying this action, it sees.
So you,
Ah,
for this
okay.
thing, I give it the actions as well, the actions. Somehow, like this. I don't want to predict the next state.
Mhm.
We can actually, that might be a pre-training because we can generate infinite trajectories for robots, for drones, and generate fake data without text to pre-train this without text.
Mhm.
But it's a different story.
Mhm.
Without that, like the direct way, without pre-training, it would be to bring text here, bring video understanding here.
Again, how did it see the previous action here?
V-JEPA didn't see
Where it sees.
here. Like here, there is this final 4-layer whatever
Mhm.
predictor. It takes as an input frames, actions, and some text.
Yeah, previous actions and text.
So the robot logic happens here, and it is not an LLM. That's what I wanted to find for 3 months now.
Actually, it's the first baseline for AVDN. In their paper, I believe, they use this kind of approach. And the game
Yes.
BERT.
Yes, 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 yes.
AVDN. Yes, this is the pipeline. The instruction is passed through BERT. Visual observation is passed through some darknet. And this is the direction. And afterwards, they pass it through this your 4-layer block. Yeah.
Except that here now V-JEPA is very strong in understanding of what's happening in the video.
Mhm.
Isn't it better based on instruction to generate gold images from intermediate gold images?
I don't know, generating images is already. No, in this case, it's like navigation, so it says like go to open a house and the are there. Generating.
Cleaning, reordering.
What I like in this architecture is that this action prediction is not an LLM. Like for these applications where you don't need
Yeah, but
context
it
instructions,
can do.
you remove this. Like for military, you just give this, I don't know, direction and something here.
Yeah. But again, if instead of JEPA, we use, let's say, Dyna version 2, why it prevented us so far? Just to get representation for each frame and
Yeah, technically it didn't. I think this sequential thing of images is what was not available in Clip or Dino. And we hope that QN visual training is bringing it. But now I'm not very certain.
in my opinion, the main influential part of this paper is that they finally get well described short vector embeddings for what is going on in the scene that helps for the forward predictor. So the main magic is not the forward predictor, but the main part of the model, V-JEPA 2. And I think my take is confirmed by the conclusion that in the other downstream task, visual question answering, it was all said that during pre-training they weren't doing language alignment, and this means that in this AGI agenda, which I hate extremely, language next to prediction is not the only thing, and they get these embeddings that mean a lot by only watching videos, and that's great. And for me, it's the main influential point of this paper.
Yeah, sure.
Well, if you ask me, this is also next token prediction. It's just for mask token prediction, but in the video space practice.
No.
It's very hard to predict a part of the picture.
And that's exactly what was V-JEPA objective, right?
Yeah, but it's not the future. It's
Yeah, it's like that.
BERT. It's like BERT
Yeah.
for video. Yeah.
Yeah, I mean, it's not very
And no language.
no language, that's important. I like it. And look, when I think about visual language navigation, you need to understand what you see, but you also need to understand what you are doing, right? What I should do in this image to get to my goal. So this relationships between images in our pipeline now is being handled by the language model. So this big language model that knows English, it also has to figure out how to connect the information from images and predict an action. That's the goal. I think in this case, a lot of that happens inside V-JEPA. So you probably do not need very powerful module on top of it. And I doubt that the language model is good for this, because language models are very strong in many different ways, but not in visual sequence understanding. The only reason QuenVL is good is because it was trained on videos at some point.
Well,
and it happened after Quen training. It's like,
I think the main argument is that when we train VLM, we align the vision representation into a language space, and we utilize LLM's reasoning ability with already aligned vision tokens. Like vision tokens can be considered here as a language tokens, kind of, because they are in the same space.
okay, that's a very good argument actually. So you say that LLMs have reasoning, and they could reason over text, and now what QuenVL is doing, they bring images and videos into this same reasoning space, into the space where this reasoning can happen, now instead of text on images.
We can also do the diverse part, bring the language representation into the JEPA space.
So what I am saying is that V-JEPA has
Has done the reasoning
has
part.
kind of visual reasoning.
Yeah. Yeah. And there is no additional reasoning for relation between different frames. But there is. Oh.
Okay, that was a good argument. I can't claim that V-JEPA's reasoning is much better than LLM's reasoning, except that it's hard to convince that LLM reasoning really transfers to visual reasoning just because of this layer, just because of this model.